organizers for inviting me to give this talk. So, just slight change of gears. I would be talking about one of the probes of the early universe, which is the 21 centimeter signal. And the emphasis would be how we can utilize this signal and what are the measurables for this signal to reconstruct some of the properties of the astrophysics of the early universe as well as cosmology. And this will be mostly geared towards our experimental efforts in trying to detect this signal. But before I dive deep into what we are really doing, just a big shout out to the team. It's an effort of a lot of people and really hard work carried out by a lot of them that I'll be presenting in this talk. Okay, so I'm sure you have come across several versions of this in this conference by now. So the kind of epochs that we are interested in this cosmic timeline ranges around this part. So essentially, this is crucial since this is the first time that we have stars and galaxies forming and therefore changing the state of the intergalactic medium. And that eventually leads to ionization of the entire hydrogen in the universe. So we have a lot of information from the surface of flash scattering, the CMB, thanks to Planck, WMAP, and all the experiments there. And we have lots of surveys going on that you probably have heard about that are targeting low redshift, and that's important in its own right, given the dark energy domination in this epoch. But this intermediate period of the cosmic dawn and reionization is something which is still poorly constrained, simply because using surveys, galaxy surveys, for example, we really are sensitivity limited at some point. And at the same time, detecting the signals that I'm going to talk about is extremely challenging because of the other contaminations that come in the picture. So our target is basically probing this using 21 centimeter signal. And just a brief schematic of what we expect to happen here. So we are looking from this part. And what we expect is formation of stars and galaxies setting at around 100 million years or so. And this is a very localized phenomena. So IgM state, it's still very neutral and pretty much non-heated. But what happens is as more and more stars form and their radiation escapes the halo is when it starts to really manifest at a very global level. And it does two specific things that we are interested in. One is heating of the IgM through the X-rays and ionization through the laminar photons that are emitted. And of course, that's a very model-dependent construct of how you look at or predict the intensity of the signal based on the nature of these sources here. But that's exactly what we are aiming to do here. And eventually, their ionization regions overlap. And at some point, you really have the entire IgM ionized. And that's the kind of universe we live in currently. We live in a universe which is completely ionized at IgM. So what we are really trying to measure is the brightness temperature of the 21 centimeter radiation. And the good part about this is we have a very fine time information. The first frame frequency of this signal is fixed, which is 1420 megahertz. And given the redshift at which we are planning to observe, we can just tune at one frequency and trying to study that epoch. So in some way, it gives a very fine information about how the brightness is evolving and therefore evolution of the astrophysical parameters itself over those range of redshifts. So the two quantities that are very important, one is the neutral fraction. So of course, when you don't have hydrogen, you don't have any brightness. But the equally important, probably more, is the spin temperature, which is this. So what we are really measuring is not the absolute temperature, but how the spin temperature acts in contrast to a background, which is this TR. And I'll focus later on what this TR can be. Right now, let's assume it's just CMB. Yeah, so spin temperature actually is a ratio of populations of singlet and triplet states of a hydrogen atom. But really, what happens is, and this is something I'll come to later, is it does couple with physical temperature. So TS can couple to kinetic temperature, which is the temperature of the gas. It can also couple to the radiation temperature, which eventually would make the signal zero. And that's what really happens in the very early parts of the universe, where everything is in thermodynamic equilibrium. We have spin temperature being actually equal to radiation temperature, and therefore you don't even expect signal from very early parts of the universe. But this really changes later, which I'll come to. So these are the two key parameters that we are trying to look at, and how it decides the shape of the signal. So this is one of the simulations which is showing you the brightness temperature of this 21 centimeter radiation. And it is definitely a three-dimensional quantity. It has X, Y, and also redshift. So the x-axis here is redshift, which is nothing but a proxy for time. And we are right here. And of course, by this time, as I said before, everything is depleted. So we really have no signal here, it's 0. But that's not been the case, especially from the onset of this star formation. You can see it goes negative first, and then it becomes positive. And that's simply because the spin temperature is, for most of it, coupled to the gas temperature. So it tracks your gas temperature and how it's cooled and heated above your background. What you could also do is take a mean across this, the spatial axis, and get a single number of what's the mean intensity at a given redshift. And that's the plot that's shown below. So this is what we call a sky average signal, or the global 21 centimeter signal. So most of my talk would focus on this part. So what happens here is, from the formation of the first galaxies, we have liminal photons, and they help couple the spin temperature to the kinetic temperature. So initially the gas is cold. So going back to this equation, gas is actually cooler than the background. And therefore you see this signal in negative, or what we say in absorption. But at some point what happens is the gas is also getting heated by the first stars and galaxies, something again I'll come to later in my talk. And that really rises this gas temperature. And at some point the gas is hotter than the background, and therefore you see this signal in emission. At this point, you also have depletion of hydrogen at a IgM level, because you have lots of these sources forming and their ionization regions overlapping. So at some point, you basically don't see a signal at all. Now, this is one model. Of course, unlike other cosmological signatures where we have a very robust template of what we are looking for, that's not the case here. This is just one model, and I'll come to what is actually the parameter space that's wide open. And there are cases where it doesn't even go to emission, for example. So there are multiple ways we could measure this. I'd be focusing on two different methods. One is measuring this mean intensity. And this is theoretically easier, simply because you don't need very fine angular resolution, which is unlike a lot of astronomical surveys. You're looking at a very large part of the sky. What you really need is a very fine absolute calibration, because in some way you are constructing a thermometer to measure a brightness temperature in the sky in presence of everything else. So this really just needs one single antenna with a very wide field of view. So technically it's easier to do, and also economically very cheaper. The other way you could do is also look at the distribution, or what's the scatter in this brightness, which you can capture by variance in the field, and how that evolves over redshift. And that's what we call as power spectrum. So in Fourier space, what you're really doing, you're measuring the distribution of power over different K modes, or different spatial scales. And that also can constrain a lot of properties of what these sources were actually. Of course, for this, you definitely can't do this with a single antenna. You're trying to measure fluctuations. You need many element system, something like this. And I'll be really focusing on both of these and what the current state is in terms of measuring these two properties. Okay, unfortunately, I can't play this movie, but what really is the takeaway message is there is a huge astrophysical parameter space, and how do you parameterize is really an open question. Different groups have different parameterizations, but the idea is that these predictions of the mean and the power spectrum both are very sensitive to the variations of these parameters. So a few that have mentioned here are basically ionization efficiency, what's the minimum mass that you need to form halos, their X-ray properties, so on and so forth. But yeah, unfortunately, this can be played. But overall, takeaway message is that the signature of this signal is a very strong function of the astrophysics. So on the left, what you see is the entire parameter space within the standard model of cosmology of what the signal can be. And you can see there are signals that are always in absorption, simply because the gas never heats up above the background. In some cases, that onset happens very early, simply because you have very early star formation happening. And And you can see there is a range of amplitudes depending really on your astrophysical setup. So from an observationalist point of view, you can look at your data and try to constrain which of these models are favored and disfavored, which is something what we have done. But that's just standard cosmology. You could also look at very non-standard scenarios. And that becomes super interesting simply because, again, from an observational perspective, you can really boost the strength of the signal. So going back to it, you're looking at the differential of the spin temperature and the background. You could boost this signal by enhancing your background. So instead of saying CMB, you can have something else, for example, radio emission from very early population of galaxies, and that would just contribute at a very wide level, which would enhance this contrast. Other way to boost the signal, like what's shown here, is you could cool the gas further. So gas is not heated by X-rays or whatever photons at all. It's cooled, but that's also a fundamental limit, which is right here around 200 millikelvin. But if you really want to go deeper than that, you need additional mechanisms to cool this gas. And that is in principle possible by dark matter baryon interactions, which I think has been talked about before. So that can basically cool the gas below the adiabatic limit, and therefore it can boost the strength of your signal. So these are some regimes of very non-standard cosmology, and they are, from an observational point of view, actually easier to constrain than the standard ones. Okay, so with this, let's switch gears and meet the experiments. So for the global 21 centimeter signal, which is looking at the sky averaged signal, there are lots of experiments going around all over the world, and actually many more coming up. I'll be talking about Saras 3, which is actually in-house designed and developed at RRI, and what we are actually doing to detect this signal. But all these experiments have a set of very common challenges. And the first challenge comes from our own galaxy. So if I go back to the signal, we are tracing the redshift evolution, and that basically corresponds to a frequency, depending on the redshift we are looking at. But at these frequencies, we do have a lot of local emission from our own galaxy and other galaxies, predominantly synchrotron. And that is exceptionally bright compared to the amplitude of the signal that you're looking here. So we're talking about 100 millikelvin in standard model, maybe a few kelvins in non-standard models. But the kind of amplitudes we have here are thousands of Kelvin actually. So this is one of the templates of what the foregrounds could be at these frequencies, and they could be really thousands to tens of thousands. And these colored signals are basically the 21 centimeter signal. So this is one of the fundamental challenges. But you could very clearly see right here is there is a lot of advantage to be exploited here in terms of the spectral nature of the two. Foregrounds are very broadband emissions, especially when you're looking with a very wide field of view, you're really diluting the impact of very specific local sources. You're looking at a diffuse emission in the sky. And that really is spectrally very smooth. While the signal, given all these different events that happen, it has lots of spectral imprints. So in some way, if you could just preserve the properties of your sky signals, you could in principle extract the signal to independent of their dynamic range, which is huge. But there are other challenges, most of it coming because we are on Earth. So this frequency range, again, is home to a lot of different transmitters around us. And really site to site, the variation is just huge. So we have actually done a lot of surveys in India trying to see which site is the most suitable. So what you are seeing is basically the measured spectrum as a function of frequency, of course, dominated by sky, power law-like signatures, mostly, again, synchrotron. But on top of that, the spikes that you see here are nothing but radio frequency interference. And based on which sites you go, it can have a drastic change. So if you're really looking at very low frequencies, which means very high redshifts, it can't be done at a site here, for example. So it's a good starting point, but that's really not the fundamental challenge. The fundamental challenge are the systematics. Of course, I can't dive deeper into it, but basically your own instrument itself can generate a lot of these spectral features that mimic the kind of features we expect in the 21 centimeter signal. And I'll come back to it because Saras has a similar kind of architecture. It's actually Saras 3 architecture. And what efforts we have put in to make sure that the instrument or the telescope does not produce the kind of signatures that we expect in the signals like these. Okay, so the first experiment I'll be talking about is Saras. This, as I said, is in-house designed at RRI, and it's been there for more than a decade now. With time, it has undergone a series of evolution, both in the way the antennas are built, the way we calibrate our telescope, all the way to the places and the media on which we observe. And the fundamental goal of this experiment is to detect this sky-averaged 21 centimeter signal from redshifts of 35 to redshifts of 6. So again, covering the whole range of cosmic dawn and epoch of reionization. And the design philosophy, as I said before, is to preserve the spectral smoothness that is there in the foregrounds. There are various ways an instrument can imprint its own characteristics in the foregrounds, and that just makes the signal extraction impossible. So this is basically showing, in absence of any instrumental systematics, if you have a foreground that is thousands of Kelvin, a signal that is a few hundreds of millikelvin, if you just remove the smooth spectral modes from the data, if your data just has foregrounds, you get down to just noise. But if you also have a signal, you do extract it out. You have basically filtered out the foregrounds by just subtracting very low frequency modes in your data. But that's not really the case when you have systematics. So I'll give just a couple of examples. For example, one is antenna itself. Yeah.
The foreground for signal.
Yeah. This one.
This is foreground plus 21 centimeters.
Yes. So what you really.
Foreground is so little, then it looks like a huge thing. I thought you told me that you said the amplitude of the signal is very small.
Yes. So the foregrounds here in the y-axis, you see around 5,000 Kelvin at the highest. So in one case, you just model the foregrounds. You don't add that signal, and that gives you this blue line here. In the other case, you add the two. So you are adding something like 5,000 Kelvin with something which is 100 millikelvin. Yeah, there are two y-axis. Right? So then you end up having a significant axis that just comes that your signal is there in the data. So yeah, so that's why spectral axis is the most important axis in these measurements. Right. But for example, one way in which this can be destroyed is your antenna has some response to the sky, the field of view, which we call as primary beam. And the primary beam can change depending on which frequency you're looking at. And we are looking at a very broad range of frequencies here. So even if your foregrounds are smooth in frequency space, because your beam is changing, it's coupling spatial modes into your frequency modes. And that can imprint a lot of spectral character. Similarly, antenna also has a coupling, right? And its coupling again can be a big function of frequency. It can vary very strongly. And that again can lead to similar imprints. So I'll not go into the details, but the overall goal is in Saras, we have tried various ways in which we can minimize those kinds of contributions. And this is what the system looks like. Theoretically, it's a very simple system. You have a single antenna looking at a very large part of the sky. Of course, it happens to also float on water to minimize some of the systematics. I'll be happy to take questions if you have. Followed by this, there is this analog receiver, which is this part. It does two things. It boosts the signals, filters it. At the same time, it also calibrates the signal because every component has its own response. So we also need to inject a standard calibrator in order to know those responses and correct for that in the data. And finally, we have a digital subsystem that takes these signals, digitizes Fourier transforms to produce the sky spectrum. So that's basically an overall structure of Saras. Now, the second edition of Saras was observing between 100 to 200 megahertz that corresponds to frequencies of around 6 to 10. So we are really probing in this experiment the end of reionization. And so this is the spectrum that we had measured. This is yet not corrected for instruments. And so the question is, if you include a model of systematics along with your foregrounds and the 21 centimeter signals, can you say something about what's favored and what's not? And that's what we did. So we went back to the signal predictions from the standard models, which is this. And just based on our measurements, we could rule out a set of these signals that are shown in colors here. And different colors are basically different significances of the rejection. So basically, this is the parameter space that we have ruled out from Saras 2 observations. So one commonality that you see across these signals are they have these deep absorptions, which means the gas is never heated above the background radiation. At the same time, you have this tail very quickly going to zero. And that basically means that the ionization is very rapid. And those are the kind of scenarios that are easy to disentangle observationally because they are less degenerate with the foregrounds actually. So those are the kinds of things that we ruled out, which is very rapid reionization with very late X-ray heating, which is very late X-ray, very poor X-ray efficiency. This work has recently been extended to also include lots of models that contain excess radio, which really boosts the amplitude of the signal, as I said before. And based on this, we can actually constrain the properties of the X-ray and radio of the early universe. So this is the blue signal. The blue part is basically the posterior, which is the allowed parameter space when you also include excess radio scenarios in the early universe. And with Saras 2 data, we could rule out a good chunk of this and actually could constrain the luminosity parameters of the early universe. So we're placing limits on how poor can the X-ray efficiency be and how high can the excess radio be for these kinds of models. So that was Saras 2. I think you have heard about edges in the past in this talk, in this conference, which is there was a claim detection at redshift 17. So now we are going to even earlier parts in this frequency axis. And it was anomalous from a number of reasons, and that made it very interesting for theoretical interpretation because ΛCDM just couldn't explain this. And this gets back to how you boost the signal. It's roughly a factor of 2 more than what's the maximum you expect. And again, the question is, can you heat the gas? Can you raise the background of the early universe, or you can cool the gas further? And these are the two hypotheses that were put forward. But the key is also it has to be self-consistent with everything else that we have. So the first was dark matter baryon interactions. So if you don't have electromagnetic interactions between baryons and dark matters, this is your amplitude that you'd get. And edges was right here. So you need some kind of coupling, but a lot of that parameter space was also ruled out before. Though there was this fine parameter space where if a milli-charged dark matter scenario of 1% of it interacting could produce some cooling of the gas, and that could match the edges signal. But of course, there are other features which are still in question, which is, for example, the flattening of the signal or its very rapid rise, because then that also ties to the astrophysics. So other question was, can you also do it in standard cosmology, but having some excess radio background? But if you do a very fine astrophysical modeling, you would see that the excesses that are produced suddenly violate all the measurements that we have in the local universe about what's the radio axis, because unless you, of course, turn them off, which is extreme fine tuning. So there was issues explaining this. We actually also put out how unique is this detection anyway. So if you have a measured spectrum and you are trying to model out your foregrounds and signal and trying to see, do you have a flat profile? Is the flat profile a unique solution, or are there better things that can equally fit the data? And turns out they could, including some of the potential systematic signatures that we know about. However, the best was to actually go out and measure it and try to verify this finding, just because it has lots of implications on early universe, both in terms of dark matter searches, but also in terms of how much radio was present in the early universe. So this was 2020, we went out measuring in the frequency range 50 to 100 megahertz. What we measured was this. So this is again, as a function of frequency, foregrounds. The great part is that edges experiment is located in Southern Hemisphere. We are in Northern Hemisphere. We have very different foregrounds. Of course, the instrument architecture itself is very different. So we tried modeling this with a prescription for our foregrounds and residual systematics using a log-log polynomial. We also included this flat profile that was detected with a scale factor as a free parameter to see what amplitudes are actually acceptable. And what we found is really the scale factor, the almost best fit value of this was actually 0. Essentially what it meant is the measurement that we have with the sensitivity that we had obtained, we could just explain it with foregrounds and residual systematics. We didn't need any kind of flat profile that was detected by edges. So we ruled that out, which means we are back to square one. Another exercise that was also very useful, I'll just skip over this, is just browsing through the whole parameter space. So we generally talk about best risk profile of 500 millikelvin, but you really have this whole range which is allowed by the measurement of edges. And we essentially ended up ruling out the entire parameter space, and we found that we are very sensitive to the amplitude of the signal, so our significance was very strongly correlated with this. Other way you could also ask this question is you take edges data, you take Saras data, and you look if there are spectral signatures that are common in both. So this is a more model independent approach, because you are not really looking for a flat profile like what edges has detected, but you take this data and what you really get as a residual is this. So the question is, it can have multiple solutions. There are multiple things that can give you this structure. So we are asking is this structure present? Yeah. No, we were limited by FM. So we just captured the rising part here, but went all the way to this part. Yeah. So when we look at this, we use exactly the same range of frequencies between edges and Saras. So we have 55 to 85 megahertz as the frequency range. So that's exactly the part that we use from edges data also. So it's exactly the same choice of frequency, same choice of foreground model. And then cross-correlating the residuals that we get to see if there is at all a correlation between them. So it's more apples to apples comparison that way. And again, what we find is zero correlation between them. And using Monte Carlo, we could see that that correlation itself was at a significance of 98%, which essentially meant not just the flat profile, but whatever was causing that spectral distortion in edges was not here in Saras data with the same set of analysis choices. But lately, we have also extended this work to include other non-standard models. So we have a joint model which has these foregrounds, some prescription for systematics, noise, and also a parameter space spanning over the 21 centimeter signal. So you have excess radio, star formation efficiency, circular velocity, optical depth. So just based on the same measurement, we could actually rule out a bunch of different 2D parameter spaces. Most sensitive, of course, was the excess radio and the star formation efficiency for that kind of redshifts. So again, this was very encouraging, and we are still in the process of observing and getting more data to better this sensitivity. So this is the current set that we have from Saras 3. As you can see, this is the parameter space. With Saras 2, we could constrain a bunch of it, and with Saras 3, we have gone even further, and we were able to constrain a lot more astrophysical parameters from the observations. But still, there is a wide parameter space which is open, especially in the ΛCDM regime, that we are not sensitive to right now with the data that we have. And that's why we need more data and probably better calibration techniques. Okay, with that, I'll just switch gears and talk about how do we do power spectrum measurement. So this was all about measuring the mean brightness of the 21 centimeter signal. But of course, looking at power spectrum is more constraining because it also has spatial information. So I'm also part of HERA collaboration. This is located in South Africa. It's a very radio quiet place. So again, it alleviates a bit of problems that we have when we observe it in India and different places. This is going to be a system of 350 dishes. And these are extremely cheap dishes, as you can see, just made of these wooden poles, PVCs, and chicken mesh. These are very closely packed, and the feeds are located right at the focus, which basically generate the current that's carried over to the electronic chain. This is still in the process of commissioning. It's getting built, but it's also observing at the same time. So the latest results that we have from this experiment actually came from a partial array. It's a very unique approach to how it tackles the challenges. Unlike other experiments like LOFAR, for example, that makes this very precise maps of the foregrounds, subtracts of all these point sources to get down to the sensitivities that we require for 21 centimeter power spectrum. HERA relies on spectral smoothness again, which means if you take a Fourier transform of frequency, which is the delay domain, the foregrounds are actually restricted to very low delay modes because they are spectrally smooth. but while the 21 centimeter signal can actually extend all the way to the very high modes. So you try your best to contain foregrounds as much as possible and just don't look there. Look at other delay modes and try to constrain your signal. So it's called foreground avoidance, and that's what Hera uses. So this is the status. The blue ones are the ones that we used actually for this result. I don't have time to go how the array was calibrated, but again, this is something I could take offline. This is the final power spectrum that we got. The y-axis are millikelvin squared instead of millikelvin. And this is the spatial scale, and this is a given redshift of 7.9. The black dashed lines are the estimates from thermal noise. So if you're seeing something which is very high from the thermal noise, you're detecting something, either it's a systematic or 21 centimeter signal. For most of it, we are actually consistent with the thermal noise estimates. Of course, we are looking at a very specific region of the sky, which correspond to some range of right ascension. Our limits can actually change depending on which right ascension we look at, which essentially means right now we can at best place an upper limit on what can be the power spectrum amplitude. And that's what we have done with this exercise. But even with that upper limit, you could actually go down and constrain astrophysical parameters. I'll skip this. This is basically the upper limits coming from different power spectrum experiments worldwide. We basically have 3 major ones. We actually started off with GMRT, which is right here. And currently we have MWA and LOFAR at the other 2 experiments, which are mentioned here. And of course, this is expected to be improved significantly once SK comes online. Hera sits right here. It's actually come down a bit lower, but we are kind of still above the theoretical predictions of the standard cosmology of power spectrum. But even at this point, we have ruled out the exotic models that include non-standard interactions. And this is a very exciting point because you're also bringing in constraints from the mean measurements from Saras. You're also bringing in the power spectrum constraints from Hera. And they're suddenly being consistent with each other. And you could also try doing a joint modeling to further improve your constraints. So for example, you could do things like this, which is the spin temperature to the background radio as a function of redshift, which is right now constrained in some way by edges and Saras. And you could bring in the constraints from Hera to, for example, do something like, what were the potential sources that could have heated the gas? Because if the gas was very low, we could have detected it, and we haven't. So you could rule out that parameter space. And right now we are most consistent with high mass X-ray binaries with very low metallicity environment that are heating the IgM. You could also look at what is the excess radio that's possible at those redshift, which is the plot like this. Of course, it needs to be taken with a pinch of salt because these measurements are at very different redshifts. So you need some kind of a model to extrapolate these to uniform redshifts. And you have measurements from the local universe, of course, extrapolated. And then those limits are getting better and better with as more and more experiments come in. So that then gives a very fine parameter space where you could work with and test different models. So that's the story with power spectrum, where we are in now, especially at RRI. So from the last deployment, we have moved on and we have upgraded our receivers. This is just the receiver response as a function of frequency access and how it changes with time. And we are getting down to thermal noise levels, millikelvin levels in the lab with the current architecture after upgrading it. So telescope-wise, we have made a lot of improvements. We are also looking at how we can quantify our systematic errors better, right? So you have an antenna observing, but it need not be stable, especially it's floating on water. So you can have a lot of artifacts just coming from the stability aspects, and how those stability aspects actually can imprint spectral characteristics. So these are spectral features in orange that come simply because of the fact that your antenna has a frequency dependent beam, which is what I alluded to before. But we're trying to basically constrain these things tight. But the last thing is also we need a better site to observe. The site that we went to, we were really restricted by radio frequency interference. So we could not go beyond 85 megahertz simply because there was FM. So we really need to find sites that are pristine. That's a very hard task, especially here. So we have tried characterizing different sites. We have a separate standalone system for that. Recently, we went down to places in Ladakh, which is supposedly the most radio quiet location. And you could instantly see the difference. So on the left, you have frequency, you have time, and these bright stripes are basically the interference, right? So you have FM lighting up the waterfall here at 100 megahertz. You have some satellites that show up here. You also have some power lines and other transmitters that show up at very low frequencies. And this is actually one of the radio quiet places. This is maybe 1 hour from here, Gauri Bidnur Field Station, which is our test bed for a lot of these first level tests. But then when you go to a site which is pristine like Ladakh, you see the contrast. There is even FM, there is hardly any. The only time you see these very blips of FM is when something, a meteor or a flight passes over it and it just reflects off FMs from very distant cities. But otherwise, you really don't see anything. Of course, you see satellites that can't be avoided anywhere on this earth. But otherwise, the kind of sites that we have located are competitive with the radio quiet locations globally, including South Africa, where Hera is located. So with that, I think I'm at time. So I'll just summarize that 21 centimeter has a lot of promise to probe both standard and non-standard cosmology. But it's extremely challenging simply because the dynamic range of the problem is very large. You have foregrounds, you have interference, you have systematics that can really compromise your chances of detection. So Saras has been addressing a lot of these, and it is in a continuous state of improvement. And we also now are getting constraints from power spectrum measurements, which are consistent with us. And we are gearing up for our next deployment sessions, which would further improve these. With that, I'll end and take questions.